Alright, hello. Welcome to a new video. We're in this problem called Path Sum 3, 437 on LeetCode. It is a medium problem, and as you can tell that I have technically solved it again, like last video. I couldn't solve it the first time because I didn't know the solution. Well, I could think of it, but it's kind of hard for me to actually implement it, so I kind of like searched it up. Thank you, Programming Live with Larry, for the solution and all the other videos I've watched. I watched the Programming Larry solution like 3 times. And some other ones to kind of understand it a little bit more, like once or once and a half. So yeah, it's a learning process. Woo! That's like an hour worth of studying. So that's awesome. So since I've studied, I just like to kind of, I guess, reiterate or kind of showcase what I've learned and want to put in my own way of thinking. So yeah, let's do that right now. Ow! Something went in my eye. Anyways, that was kind of weird. Alright, so let's kind of solve this using my own problem solving process with this problem. So let's kind of read the problem. So, given the roots of a binary tree and an integer target sum, return the number of paths where the sum of the values along the path equals target sum. The path does not need to start or end at the roots of a leaf, but it must go downwards, traveling only from the parent nodes to the child nodes. Okay, so that is an interesting problem. So just to, before I kind of reiterate the problem, let's just kind of intake what the input and output is. So the input's basically tree node, the roots of BT, and then we're also given an integer, so int target sum, and then for our output. For output, we're supposed to return int, and it's supposed to be the number of paths that equal to target sum, right? And so to note, it's very important that we note that a path can start at any node, not just the root. I feel like if we can only start from the root, this problem would be easier, but it's a medium problem, I guess, because we can't start from the root, which is interesting. So yeah, let me think. Is there anything else? Return the number of paths where the sum of the values along the path equals the target sum. Okay, so I'm not missing anything. I guess some questions I can ask is like, what's the min length BT? We can just scroll down, and then what is the min value of node in BT? So those are my 2 questions. So the min nodes is basically 0, and then the min value of each node can be infinity, so negative infinity, I guess. And then I didn't think about the target sum, actually, like as that for a question. But that's interesting to note that the target sum can be negative 1000 up to 1000. I don't think it really matters either way. So yeah, those are my questions. So I guess we can do an example, right? For this case, I kind of like to just copy this example, just for sake. So what do they have? That 10 5 3 3. So 10 10 5 3 3, and then 5 2 1 5 5 2 1, and then what is that, negative 2, and then 10 negative 3 11. And they point like this, right? Boom, 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 boom. All right, anyways, and then they have our target sum to be 3. So I guess TS is equal to 3, target sum, right? Or I can just say it, target sum equals 3. Right? This is our target sum 3, and we kind of want to find a path where the target sum equals to 3. So yeah, just go through it as like we're just doing it for the first time. So what I can see, wait, is there a negative? Okay, so 3. What's the target sum that adds up to 3? Wait, oops, target sum is 8. Oopsie, my bad. I was just looking at it because I was trying to look for a target sum equal to 3, but I saw none. So no, well, there's one. There's only this one, right? But anyways, target sum is 8. So what's the target sum that equals to 8? It can start at any node. Doesn't have to be the root. But I think fortunate enough for us, was that 10 minus 3? That's like 10 minus 3. Wait, 9. Oh, okay. So target sum equal to 8. Okay, so 5 plus 2, that's 7 plus 1, that's 8. So that's one right here. That's cool. And then is there one here? Wait, 10, 9, 8. Okay, this one right here, 11 minus 3, 10, 9, 8. Yeah, that's correct. And then anything else? 6, 7, 8. Yeah, so we also have one right here, so that's 3. So we're going to return 3 as our answer. Right? So if you do it in your head, it's easy, but not for me because I can't do mental math in my head that easily. But if we just write it down and kind of keep notes, no matter what node we can start at, we can find, we should be able to find like we should be able to find like the target sum if we just go through a path, right? So in this case, it's 3. So that's cool. So yeah, that's kind of cool to note. And then I think it's also kind of cool to note if we actually kind of run this as a computer. So in the case that we start from the root, we'll have, yeah, in the case where we start from the root, we also have these, right? These are our targets, target sum paths, right? If we start from the root, if we're like a computer, right? So obviously we just go here, we go here. So we start starting from the root, right? So we all start from 10, right? So if we actually kind of calculate these, so if we do like 10 minus 3 plus, I can just do like, wait, what? Isn't that like, wait, I need a calculator. So 10 plus 11, that's 21, minus 3, that's 18. So here the actual running sum of it is 18, right? This is 18. And then I think this one's also 18. Wait. Yeah, this should be 8. This should all be 18, right? It's all 18. I'm pretty sure. No, there's no way it's 8. Wait. I need to do some math. It should be 18 because it makes sense. Because what I'm about to explain, 2 plus 1. Oh, no, this is 21. Oops. Wait, am I wrong? Wait, 10 plus 5 plus 2 plus 1. That's 18. Okay, cool. So these all add up to 18 if we include the root, right? But as you can see here in the green, if we basically remove the roots, then we'll get 8 because 10 minus 18, that's 8, right? Does that make sense? So yeah, if we basically remove the roots, if we find out a way to remove the roots in this case, then we'll be able to find our target sum, right? So this is 18 minus 8. That's what we're kind of doing, right? As you can see, we can kind of convert this into target, into running sum minus target, right? Right? Because either way, our green is our target sum and our blue is our running sum that we calculate with the root that we start at. So if there's a way where we can basically remove a part of our running sum, then we'll be able to find a target at any node. So yeah, we gotta keep track of that somehow. And even though I don't really understand it quite well, as I can bring up from my mind like perfectly, it's something about like a prefix sum where we kind of keep track of all the running sums that we have right now minus our target. So basically, if we start at 10, right? We start at 10. 10 is basically a path already, right? So it's technically a part of our path already. So we can keep track of that 10 does exist. And so if we basically say that there's such a thing where 10 minus 8 is equal to some path, Yeah, so if we basically say that it's our running sum minus target is equal to some, not some, but like some path that we have already seen, then we can basically say that that it's true, that we can be like, okay, so this running sum that we have now is basically valid, that it can be equal to the target if we just remove some path that we've already seen or have been through already. Well, that's how it makes sense in my mind. But if not, then I don't know. My bad, I guess. But everyone has their own way of understanding it. That's how I understand it. So yeah, it's kind of cool. So if we take that into account, we can kind of like code it in a way where it makes sense with that logic. So we've done an example. Now let's go ahead and kind of match. So what I said again, prefix sum, where in such that running sum minus target. So we can say if running sum minus target is equal to some path already taken, then it's true. And it's true that we can remove some path to equal to target sum. Right? So yes. And then we can count that as so we can count that as path that equals to target sum. So yeah. So yeah, so that's my logic that I'm going with. Yeah. And so that's one match we can do. We can also do some recursion. Obviously, because we're dealing with a binary tree. I'm pretty sure you can do like a stack or something like that, or like breadth first search or whatever, but I'll just do recursion. I don't know. Because that's what I'm learning right now. And then what else? We'll obviously have like a running sum counter. To keep count of sum currently at node. And then we can also have like a dictionary. And this dictionary will help us keep count of paths already taken. Yeah, paths already taken. Paths already taken. So yeah, that's cool. I could be wrong on that, but it does make sense to me. Right? That does make sense to me. So yeah. So I think in this case, we kind of already have our tool set up for us. We just gotta code our tools. But before I code, let's make a plan first. And before I make a plan, I want to go ahead and make my pseudocode. So I'm gonna name this function get paths. And it's gonna take in our input, which is our root, and then target sum. And I'll pass it for now, and then I'm going to make our tree node class. Oops. And then I'm gonna make our driver code. I think I want to make it like this, but I feel like it'll be too long. So I think I'm just going to do it up to, honestly, I'll just do it up to like right here. All right. So in this case, we should get like 5, 5, and 3. So we should get like a value of like 2. So I guess we do like no, I'll just do the whole thing. Well, it's be long. I'll just pause it here. All right, so I made my driver code, just this whole tree in driver code, and then I'm going to basically, I know that we're going to output an integer, which is number of paths. So I'm just going to print out the result of what we return. So we get paths with root and target sum, which is basically going to be like 3. No, it's gonna be 8. Oops, my bad. So that's right here. Target sum is 8. I don't know why it's 3. It should be 8, right? So, yeah. So now let's go ahead and make some pseudocode of what we want to do. I'm going to basically make our pseudocode into like comments in our code. And then once we're done, I'll just paste it in here in this huge comment block, so we can actually code it. And we'll just follow along with the plan that we paste right here, right? So that's what I'm going to do. So what's the first thing I want to do in this code? First off, I want to initialize like a counter, as we said. No, as I didn't say. I want to set up a counter. So counter is equal to, our result is basically equal to 0. And I want to set up a dictionary. So count dictionary is equal to, I can say, what's a good name for this dictionary? Path so far. Path sums is equal to a dictionary. So counter dot collection dot counter. And then once we have that, we can basically go through some depth first search with DFS, and then this is going to take in the node that we're at, and then the running sum that we have right now in the node, right? So from there, in the end case, we obviously want to go through the left and right. So left, running sum, and then the right. We obviously want to go there, right? And then what do you want to do? So as we're going through recursion, I want to keep note of our running sum right now. So I'm gonna say that path sums at a running sum is going to equal to, is going to increment because we already seen it, right? And then we can say that the running sum right now is going to equal to the node value as well, right? Once you have our running sum, we kind of want to check if the running sum minus target is equal to some path that we have right now. So, and the running path some path is equal to, yeah, the running path the sum path is equal to the running sum, actually. So, no. Oops, that's wrong. So we want to check. We want to check if if running sum. So if path sum. So if we basically find the path sum at this key that equals to this formula, which is running sum minus target sum, right? Equals, yeah, so if we basically find it. So if we basically find it, that means that we have found a path that equals to our target sum. So basically, yeah, this basically this green. Yeah, so this formula is basically this green, right? Where we kind of remove this, right? Because we basically found it. So we just kind of say, okay, so then this green path that we have right now can equals to some path. No, is equal to the target. Oops, my bad. It's kind of confusing, sorry. And so we can basically increment our count by saying that, yeah, we found some path in our way when we've calculated the running sum minus our target, basically the prefix. And so, yeah, we basically found the prefix. So that means that there is some path that we can subtract from our running sum, and we'll get our target with our running sum that we have right now. So we could increment how many times we've seen that that we've seen it, right? Because in this case, if we start from 10, if we follow this code, if we start from 10, we basically add 10 to our path sum plus 1, meaning that we've encountered this as some path, right? So if we've seen some path in our running sum when we minus our target to get our prefix, then yeah, then we can say that our running sum minus our sum path equals to our target, which we found right here as a target path, as our target sum path, right? And so I don't know, what I'm saying is kind of confusing even to myself too, but it just makes sense to me. Maybe I need to explain better. But yeah, that makes sense, right? In some way that it does work. And then in that way, in the end, we need to, oops, I think this is right. In that way, we need to basically add our path sum we have right now of our running sum into our path sum that we already seen, right? And then in the end, we need to kind of subtract it. Oh my god, I'm sorry. I'm talking too much. We need to subtract it because this dictionary is only for a singular path that we've already taken, right? So basically, if we go down here and we say that we've found yeah, if we basically go say down here, we have like some path already incremented once, right? And then it's somehow found here again. I'll be wrong because see, this is like 1 and then this is 2, right? It's gonna say that, okay, we're gonna increment our count of our result by an extra 1 because we found one in here, but we only want it for this case where we go along this path, right? So we don't want to like extra add because it's a binary tree, so we can go either way. And so since our dictionary kind of holds like everything, it holds our whole tree, right? It holds our whole tree. We kind of want to limit it to one path. So once we're done recursion with one path, we kind of want to block it out. So that's why we say that we're going to subtract the sum path that we found, right? So yeah, if this was a linked list, I don't think we need to do this at all, right? But since this is a binary tree, we kind of want to block out like some certain paths from certain other paths, because that wouldn't make sense in the code, right? Or like logically. Because we can't find some path. We can't find some path in this path. So yeah. So yeah. So we kind of just have to code it up like that. And then in the end, we should have our result to have the correct number. So what we're going to do, the correct number of paths. So what we're going to do is we're going to return res. Return res, but before that we have to call DFS with the root and 0, because 0 is our running sum so far. So yeah. So we can copy that in code to our plan. Right? You just kind of copy this as you see fit. So res is equal to 0. Then our path sum is basically equal to I can just say it's some path. Then I gotta import collections. Then we had to do that for search. Node takes a node and the running sum that we have right now. And then we have to say, so if not node, if not node, then just return. And then if that's not the case, we just solve it. So we say that the res, res plus equal to some path, and our running sum is target sum. So basically, if our running, if some path is found to have like is found or we've already seen, we add it to our result by 1, and then we add our running sum that we have right now. Oops. I should say that the running sum gets incremented to our node value that we're at right now, and then we can add some path, which is our running sum, into the dictionary and say that it is there, that we've already seen it. Then we can go that for search with our left and right with the running sum that we've calculated. And then once we've already gone through the left and rights of those, basically when we've gone through the whole path, we can basically remove that running sum from the sum path that we've already seen, because we don't want that to carry over onto the next path that we go through. And then once we're done with that, we've kind of coded our depth first search already, so we can call depth first search and give it the arguments of the root we're given and 0, which is the running sum that we start off with. And then we can return res. One thing that we're missing is that we need to initialize some path at 0 equal to 1, because there could be a case where there's a running sum. No, there can be a case where our running sum minus our target could equal to 0, and so we can just say that that path can exist, I guess, where it's like 10 minus 10, right? our running path is, our running sum is 10 and our target is 10. Yeah, target sum is 10. Then we can say that, yeah, it's there. So yeah. That 0 is there. That is some path, right? So yeah. I don't think I explained it correctly, but see, I don't know. Yeah, this should work. So I guess we should get 3 back. This does work. Plus equal to, can I also access for, oh, can I access local variable? So I have to say that non-local, that res is non-local variable, because we want it to reference this one. Okay, 3, so it does work. Alright, cool. So I'm gonna copy and paste this into LeetCode. Should work. Run. Accepted. Submit. Accepted. Cool. So that's my explanation. To be honest, this was kind of like a hustle. I think it's mostly because it's a binary tree. I feel like if this was, because I'm definitely sure that I've done prefix sum, but it's done in a way it's in a binary tree, so it's kind of hard for me to kind of navigate the problem. But I do get the concept in that if this was like a list, so say like 10, 5, 2, 1, if this was a list, right? Then I can say that we can find our target equal to 8 if I just kind of keep track of the running sum that we have right now. So running sum is equal to like 10. We found 10 already. And then 5. No, some like sums, I guess, or sums, I guess. Right? So 10, 1, and then we have like 15 once, and then 21. No, 15 and 17. 1 and 18. And then our running sum is like so we can say that like target is equal to no, if our target is 8, and then we can do like running sum, which is like 18, and then if running sum minus target is in sums, and return true, just something like that. Like it makes sense. So yeah, it makes sense to me. Like that's the case where there is our target in this list, which is O of n time. So yeah, I just want to make sure like I do understand like the prefix of it, the prefix sum part of it. Okay, so I was looking at an email. So yeah, for time complexity, it's O of n time because we go through each node once. And then for space, it's O of n because we store every node value in a dictionary. So yeah, not every node value, but every like running sum of the nodes that we have into. Yeah, so yeah. Yeah, that's pretty much it. So yeah, hopefully I've learned something. Well, I did learn something. Hopefully you learned something maybe. I don't know, but yeah.